So next, I would like to bring on stage Wai Tong, current PhD student at Stanford, and graduate fellow at HAI, the Institute for Human-Centered AI. And Wai Tong will share with us his ongoing research work with his thesis advisor to do with industrial and environmental reacting flows. What those mean, I leave it to Wai Tong.
Yeah, nice to meet you guys. As our wonderful host has said, I'm a PhD student at Stanford University, so welcome. I'm also affiliated with the Stanford Institute for Human-Centered AI. And today I'm going to talk about the potential and challenges of machine learning in industrial environmental reacting flows. And these are a couple of slides that me, myself, and my PI, who's in the other room at the moment in the executive session, have made to just give a broad overview of what the field is, what the potential challenges in the field are, and how AI can help in solving some of that. So let's start with why I care about reacting flows. Now, I know why I care about reacting flows. Reacting flows are great because they're an intersection of complex math. We deal with a lot of PDEs, like namely the Navier-Stokes equations. I get to use supercomputers all the time to solve problems tied to that, so that's really fun. And it's a nice intersection of flow physics and reaction chemistry as well. So, if you're a science nerd like myself, you'd really appreciate that. But, I shouldn't really talk about myself in this presentation so much. I should care about the audience too. And here are some reasons why you might want to care about reacting flows. And first reason for that is because of energy conversion and propulsion. Fossil fuels currently occupy 90% of the energy ecosystem, essentially. And so, if you care about jet engines or rockets, which are really cool devices, you'd want to care about reacting flows. Next, a lot of these fossil fuels, they have a lot of nasty pollutants. So we're talking about nitrous oxide, which can cause acid rain. We're talking about soot, which can reduce your life expectancy. And of course, carbon dioxide. And how you deal with a lot of that in carbon capture strategies or catalysis is also part of reacting flows. And then there's also natural hazards, stuff that we can't really do much about from an engineering perspective, but we can mitigate. So wildfires, risk assessments associated with that, models to know how destructive they can be. That's a reacting flow research topic. And of course, there's chemical processes tied to that too. A lot of our members in industry care about chemical processes to make fertilizers or plastics or synthetic things. Those are all reacting flow processes. And of course, putting out fires too in in a building fire. You really have to know how halogens and other things that can put out fire behaves to really create good fire extinguishers or fire management systems. So I'm going to focus my talk around one of the biggest challenges in I think the world and also my field at the moment. Of course, climate change, global warming, huge elephant in the room. And this is a nice International Energy Agency outlook pie chart on what the energy landscape would look like in 2050 and what needs to be done to achieve that. And within reacting flows, we have, of course, hydrogen is a huge part. How you make that, how you burn that, that's a huge part of our research. Renewables, so biofuels, electrofuels, when you take solar and wind energy and wave energy and you create synthetic fuels with that energy, that's also another potential application of my research. And electrification too. We have a very nice talk about batteries from Professor Chao Hu before this. And it's tied into that because some novel concepts such as lithium air batteries really rely on reacting flows. And of course, carbon capture and storage. This is a huge part to deal with the existing energy ecosystem that we have today. So a lot of fossil fuels have a lot of carbon dioxide. You could either let that go to the atmosphere where it's going to do very bad things, or you can put it in the ground where our problems are solved. So in terms of handling this challenge, we can break down the energy landscape into 3 different sectors or problems. First is problems tied with energy production. Next, we have problems tied to energy storage. And then we also have problems tied to the way we consume our energy. And I'm going to talk about the AI that can go into some of this. And so before we go into AI, we need to talk about data. And let's talk about gas turbines in general. And because it's one of the most commonly used applications of energy consumption. And gas turbines, you can find them on planes. And each of these engines can produce about 20 terabytes of data per engine per hour. And there are 2 of them typically on a plane, or 4, depending on the plane that you're on. And for a 6-hour flight, let's say, from JFK to LAX, you have 6 hours of that. And then there are 20,000 US daily flights, basically. What you end up with is 4.8 exabytes of data a day. And that's how much data we have in reacting flows. So you can think that this is a huge avenue for AI, and you would be right. So let's talk about AI and energy production first, the first sector I talked about just now. In terms of what's been applied, you've seen companies like Total work with Google on existing computer vision algorithms to really figure out how to optimize their oil extraction problems by really taking advantage of subsea imaging and applying AI to those problems. You also have problems like predictive maintenance, which I think is a huge theme in this conference itself, where you see different companies such as Pepsi and Colgate really apply organization scale algorithms to apply to factories. And this can be applied to companies that create energy for us too, whether it's hydrogen or fossil fuels or solar or wind. And of course, tied to this is intelligent control as well. Recently, there's a huge headline of how a chemical plant in Japan has basically applied AI to solely control their chemical plant for 35 consecutive days, which is pretty impressive because you would be able to reduce a lot of human costs with that. And in terms of energy storage, a huge application for this would be materials discovery. And I want to show you first this plot that I've taken from The Economist, and it really shows what one of the big challenges in the energy transition landscape is. I want you to pay attention to 2 points within this chart, which is namely diesel and petrol over here, which has a lot of energy per volume. So a liter of it has a lot of energy, and hydrogen, where a liter of it doesn't have a lot of energy. And the reason why hydrogen isn't as popular as fossil fuels at the moment is because it's really hard and expensive to transport something with so little energy density to the devices that we consume. So what AI can do is that it can help us discover materials that can really improve this energy storage. And this is a recent work in the Patterns Journal published recently of how AI is being used to discover which materials can really bind with hydrogens to really improve that energy density. And this is not a problem that's solely being investigated in academia. We have members of industries such as Meta AI trying to accelerate this process by assembling data sets around this. And I'm going to talk about this last section of AI applications, which applies to digital twins or simulations. And this is something that I work very actively in my research and my lab. And so what would you use digital twins for? So in the process of carbon capture, you would basically try to understand what geometry, what material works really well in capturing and binding carbon dioxide, essentially. In terms of batteries, you would really try to figure out which molecules, which ratio of chemicals, which materials really improve the effectiveness and efficiency of these batteries. In terms of traditional energy systems, such as gas turbines, we have a huge push to decarbonize them, switch to carbon-free fuels, such as hydrogen, which only produce water and not CO2. And so with that, these digital twin simulations can really help us transition to that by helping us assess the safety of doing this. Because as we all know, with the Hindenburg disaster, hydrogen is a very dangerous fuel without the right engineering, but with the right engineering, it can be very safe. And so how AI can help with this is that a lot of AI is now focused towards spatial temporal predictions. And I think the most common application you can think of this is when you use AI to try to predict videos on YouTube, like predict the future from like a training set. And some of this technology is currently being applied right now, but we still need to figure out, it's not really that popular yet because we still need to figure out how to make them guarantee physical laws, because they're not really doing that. It's mainly a statistical correlation at this point. But I'm going to talk about that in a little bit. Because despite all these interesting applications, we only apply about 13% of AI in industry. Most of the problems being applied in AI right now are in natural language processing and computer vision. And I'm going to try to examine why. Okay, so most of the AI algorithms we see today, they're typically in the form of recommender systems or language translation algorithms, and these are mature technologies being used by the mass market. There's a lot of people using them. But the applications that I talked about just now, they're either applied to targeted communities, such as labs in academia, or organization scale, where you apply them to a factory and not really you don't really share the technology with other people. And I just want to spend the next couple of slides talking about why these applications aren't easily commercialized. And this really falls into the theme of this conference, which is knowledge first AI. And so towards mature AI, what do we need to do and what are the challenges to reach this? We have to consider the fact that we're dealing with safety and critical systems. We're dealing with integration with human capabilities as well. And so let me just start out with showing you this plot over here. This is the famous ImageNet challenge. In 2015, this really kicked off the deep learning circuit. Everyone cares about machine learning now, partly because of the results from this challenge. And it's primarily because He et al. Created ResNet, and they managed to show that it could beat human performance in image recognition. So this 3.6 error is way better than a 5% error in terms of human capability to recognize images. But do I really trust an algorithm with a 3% error to build a rocket for me? That's a huge question, because those rockets have people in them sometimes, and then those people are very important to us, so we don't want anything bad to happen with that. And these rockets also cost billions of dollars, and we really don't want anything to go bad in this. So the question is, how do we solve this? And I believe that a huge solution to this is to involve human knowledge in the loop. And how we can do this is using three aspects. So I wouldn't necessarily trust an AI to build a rocket from scratch, but I would trust an AI to give me prototypes of what the rocket combustion chamber would look like. And then I could put that through several tests to figure out, like, oh, if this works or not. I would trust the AI to create new materials for me, or suggest new materials for me, which I can then test robustly with human systems. I would trust the AI to give me simulations, which I can then validate with human systems. So it's important to identify non-critical components tied to human safety. The other aspect of it, and I'm pretty sure this has been discussed throughout the conference, is the concept of interpretable AI. If I have an AI that isn't a black box, but a gray box or a white box, it would be much easier for me to identify what's wrong when it makes a false prediction. And there's huge progress in this in natural language processing, because AI auditing is a thing. You want to be sure that your AI model isn't predicting any like harsh or dangerous language. But it's also being applied hugely in other fields as well, especially in the sciences, where you really want to know why the AI is behaving this way because you don't have equations to guide them. The other aspect is to embed human knowledge, and this ties into the 6 strategies of physics-informed machine learning that we saw in the previous talk, where you use your understanding of physical laws or like empirical knowledge of like a system, and you change the architecture, you change the prediction target, you change the data, and so there's obviously a lot of human knowledge solutions that could go into AI. And so these are the 2 topics that are very tied to this conference. But I want to bring up 2 other issues which we shouldn't forget, even though this is a knowledge-centric conference. And it's to do with computational complexity and data availability. And the reason for that is part of the reason why deep learning is so powerful is because there's a ton of data available. Let's say those 4.8 exabytes. You need the computing power to process that. And this has really pushed a huge direction for the private sector to have increased computing power. This is a very nice slide from State of AI that shows that companies like Meta and Tesla now have more GPUs than the most powerful supercomputers in the EU and the US. So that's Leonardo and Perlmutter, which I may have opportunity to use for my research in the future. It really shows you how expensive AI can be once it reaches a certain level of maturity. And this is really shown by natural language processing models, such as GPT-3, which have 175 billion weights in them, and they cost about $5 million to train. So knowledge-centered AI, I think, is very important so that you can lower these costs, because if you were to rely from a pure data approach, this is the cost that you're looking at. Another challenge that I want to talk about is, of course, data availability. And this is a survey done by Dimensional Research with 227 participants from industry. And it shows that one of the major challenges that they have with the data is that either the data is poor quality or that they don't have enough data. And this is an avenue that I think that knowledge-centered AI can help improve to too. But I want to bring up another paradigm that goes with this, and it's the open source nature of a lot of AI technologies. A lot of people here have probably heard of PyTorch or use PyTorch and TensorFlow. They're open source code that everyone has access to. They're great for people like me who started my PhD 5 years ago and just really want to go into AI. It's just code that I could use very easily and accessible. AlphaFold is always in the headlines because it solved like a 50-year grand challenge in biology. And this was done because of open source like data sets built together by DeepMind and various governments around the world to really assemble these data sets. So there's a huge open source component to this too. And of course, models such as Stable Diffusion, which generate images purely from just inputs and outputs from machine learning, these models are also open source, and anyone can use them and play with them and do transfer learning or anything on them. And so there's a huge open source element as well in AI. Now, tied into this is data sets such as ImageNet, as I brought out just now. And this is what a mature data-centric data set looks like. This is 120 gigabytes. In 2009, at 15 million images. I think today it has more. Versus a fluid physics data set in my field known as Johns Hopkins data set with only 9 configurations. But these 9 configurations are not arbitrary. They're still about 500 terabytes. So there's a huge effort that needs to go into creating more data for people as well as improving the knowledge. These are not competing paradigms, but parallel efforts that probably should go together. And this can be made much easier through collaborations. And we're seeing a lot of collaborations from governments and academia, between governments and industry and industry and industry. And this ties into one of the works that I'm doing in my lab, where we're trying to make 20 terabytes of scientific simulation data public. And this approach is through communicating with different experts around the world who have a lot of data and a lot of knowledge, working with them to compress and upload those data sets to a repository that we can reach in. And we're currently, this is a very active aspect on this. The URL isn't here, but if you search up my name in Google Scholar, you can find this work that I've published recently. So this is collaboration that I've done with various organizations, at Stanford, Sandia, University of Connecticut, Melbourne, and Montreal Polytechnic. So I just want to wrap up this presentation with some of the things that I've talked about. Energy is one of the big challenges in reacting flows, and we care about a lot of problems in production, storage, and consumption. I've talked about the 4 solutions that can help accelerate this and make the technology more mature, and it's to consider safety and critical systems by integrating with human knowledge and human capabilities, and to also not forget about the computational complexity and the data availability that challenges that we can find in this field as well. And I just want to end with a note of what the energy landscape kind of looks like, because my talk is centered around this. So currently, this is what the energy use in transport looks like. Most of it at the moment is with fossil fuels, around 80 or 90% if I'm not mistaken. So with government regulation, by 2050, this is what it's going to look like. So we're going to drop our fossil fuel dependency to about 50%. Not quite enough to hit the 1.5 Celsius target that a lot of the governments have been talking about. But I think with emerging technologies, with accelerating AI, with all the efforts from different industry collaborations, government collaborations, and academic collaborations, we can hopefully reach to a day where we can really have a net zero dependency on the current energy landscape. So thank you.
Awesome. Thank you. We have time for 2 questions.
Awesome presentation. Question is, have you worked with exhaust gas capture technology with your work, and if so, where do you think are the biggest areas of improvement to incorporate machine learning and AI in that technology?
So I personally have not worked on carbon capture that much. I think we have like 5 members of our lab working on that a lot. AI can really help with that. I think, like I mentioned before, it's currently in digital twins and probably materials discovery. So if you can discover like material that can really bind with carbon dioxide really well, you're really creating a place to store that, right? Or discovering chemical processes that can convert that CO2 into just pure carbon and oxygen, right? That's a nice idea as well. So it's probably around there. Otherwise, like classic digital twin stuff to figure out what kind of geometry of pores in the ground really are useful for storing carbon dioxide. That element as well is probably where AI should go.
Thank you, Wai, for the presentation. There are one question from the online viewers. The other, have you done any use case with machine learning for the existence SCADA for flowback operation for oil and gas industry?
Not for the oil and gas industry. So my research is primarily more in the fundamental side. So trying to figure out a lot of the physical processes that go with it, using machine learning for model discovery. The closest thing that I've done to that is assembling this 20 terabyte of reacting flow data sets. That kind of data set can really be transferred towards applications in the oil and gas industry, I think.
Thank you very much. It's a great talk. And again, everyone, please find ways to vote for your favorite talk in the symposium. There will be a prize at the end of today's session.